everyone, I am MD Sathya and my teammate is M Spandana. We made this presentation under the guidance of Dr. M Prasad Sir, Associate Professor, Department of CSE. In this presentation, let's know about the critical section problem. A critical section is a segment of code which can be accessed by a single process at a specific point of time. The section consists of shared data resources that require to be accessed by other processes. The entry to the critical section is handled by the wait function. The exit from a critical section is controlled by the signal function. Here, n processes competing to use some shared data. No assumptions may be made about speed or the number of CPUs. Each process has a code segment called critical section in which the shared data is accessed. Problem ensures that when one process is executing in its critical section, no other process is allowed to execute in its critical section. When a process executes code that manipulates shared data, we say that the process is in its critical section. The execution of critical sections must be mutually exclusive. At any time, only one process is allowed to execute in its critical section. So each process must first request permission to enter in its critical section. There are four essential elements of the critical section. First one, entry section. It is a part of the process which decides the entry of the particular process. Critical section. This part allows only one process to enter and modify the shared variable. Exit section. Exit section allows the other processes that are waiting in the entry section to enter the critical section. It also checks that the process that finished its execution should be removed through this section. Reminder section. All other parts of the code which is not in critical entry and exit section are known as the reminder section. Here there is the general structure of process PI. Here processes may share common variables to synchronize their actions. Critical section problem must satisfy three requirements. First one, mutual exclusion, and the second one, progress, and the third one is bounded waiting. Mutual exclusion. If process PI is executing in its critical section, then no other process can be executing in their critical sections. Implications. Critical sections better be focused and short. Better not get into an infinite loop in there. If a process somehow waits in its critical section, it must not interfere with other processes. Progress. If no process is executing in its critical section and there exists some process that wish to enter their critical section, then the selection of the process that will enter the critical section next cannot be postponed indefinitely. If one process wants to enter, it should be able to. If two or more want to enter, one of them should succeed. Bounded waiting. A bound must exist on the number of times that other processes are allowed to enter their critical sections after a process has made a request to enter its critical section and before that request is granted. Assume that each process executes at a non-zero speed. No assumption concerning relative speed of the n processes. Let's know about process synchronization. Process synchronization is a task of coordinating the execution of processes in a way that two processes can have access to the same shared data and resources. It is especially needed in a multi-process system when multiple processes are running together and more than one process try to gain access to the same shared resource or data at the same time. This can lead to the inconsistency of shared data. So the change made by one process not necessarily reflected when other processes access the same shared data. To avoid this type of inconsistency of data, the processes needs to be synchronized with each other. Now let's know about the Peterson solution. Peterson solution is widely used solution to critical section problems. In this solution, when a process is executing in a critical state, then the other process only executes the rest of the code, and the opposite can happen. This method also helps to make sure that only a single process runs in a critical section at a specific time. In Peterson's solution, we have two shared variables. First one, Boolean flag I, initialized to false. Initially, no one is interested in entering the critical section. In turn, the process whose turn is to enter the critical section. Peterson's solution preserves all three conditions. Mutual exclusion is assured as only one process can access the critical section at any time. Progress is also assured as a process outside the critical section does not block or other processes from entering the critical section. Bounded waiting is preserved as every process gets a fair chance. Synchronization hardware. Sometimes the problem of the critical section are also resolved by hardware. Some operating systems offer a lock functionality where a process acquires a lock when entering the critical section and releases the lock after leaving it. So, when another process is trying to enter the critical section, it will not be able to enter as it is locked. It can only do so if it is free by acquiring the lock itself. Mutex locks. Synchronization hardware, not simple method to implement for everyone. So strict software method known as mutex lock was also introduced. In this approach, in the entry section of code, a lock is obtained over the critical section resources used inside the critical section. In the exit section, the lock is released.
Test and set is a hardware solution to the synchronization problem. Here, test and set, we have the shared lock variable, which it can be either takes two values, that is zeros or ones. Before entering into the critical section, here the critical section process inquires about the lock or requires about the lock. If it is locked, it keeps on waiting till it becomes free, and if it is not locked, it takes the lock and executes the critical section. So here is the test and instruction that can be defined. First we take the boolean value test and set. We set the target, and boolean value is assigned to the target, and the target is, if it is true, it returns the boolean value. The important characteristic of the instruction is that it is executed automatically. It thus, if two set and test instruction are executed simultaneously, that means each on a different CPU, they will be executed sequentially in some arbitrary order. If the mission supports the test and set instruction, we can implement mutual exclusion. So the structure of process PI shown according to the a critical section is a segment of code which can be accessed by a signal process at specific point of time. It is the part of the program that accesses shared resources. Only when a process is in its critical section can it be in a position to disrupt other processes. We can avoid race conditions by making sure that no two processes enter the critical sections at the same time. where the resources may be any source in computer like memory location, data structure, CPU or an IO device. Critical section segment cannot be executed by more than one process at a time. That critical problem is used to design a set of protocols which can ensure the race condition among the process will never race. In order to synchronize the cooperative process, our main task is to solve the critical section problem. We need to provide a solution in such way so the segment is provided here. The only single process. Now let us talk about the requirements. There are three requirements: mutually exclusion, progress, bounded waiting. Mutual exclusion. It is a process in executing in its critical section. Then no other process is allowed to execute in the critical section. A program object that prevents multiple threads from accessing the same shared resource simultaneously. A shared resource in the context is a code element which critical section, the part of code that should not be executed by more than one thread at a time. Progress. If no process is executing in the critical section and other processes are waiting outside the critical section, then only those processes are not executing in the remainder section can participate in deciding which will enter in the critical section, and selection cannot be postponed indefinitely. Indefinitely. Bounded waiting. There exists a limit as how to process can get their critical section after process request entry into the critical section and before that request is granted. In bounded waiting, there exists a bound or limit on other number of times other processors are allowed to enter the critical section. For example, while P is waiting to enter its CS, other processes may be waiting as well, and some processes executing in its CS. When it leaves its CS, some other processes has to be selected to enter the CS, which may or may not to be P. Suppose a process other than P was selected, the situation might happen again and again. That is, other process getting a chance to enter CS but never P. Note the progress is being made, but other process not by P. The problem is that P is not getting the chance to do any work. So this occurs to prevent a starvation must guarantee. The process of creating the software consumes a lot of time as well as updating the system. These software systems may sometimes not cater for all requirements of the user. This is also costly when it comes to obtaining license. When the system failures, OS is considered to be heart of the computer system. So it is expensive. The operation comes with heavy price and comparatively expensive compared with OS like Linux, virus threats, reliability, etc. So the critical section has some drawbacks. The use of critical section in a program can cause a number of issues including deadlock. When two or more threads or processes wait for each other to release a critical section, it can result in a deadlock situation in which none of. Thank you.